Hello, everybody. Welcome back. Today, we're going to be talking about radical halogenation. And so, this is the part of the course where we finally gotten into reaction chemistry, and this is also the part of the course where I would say things get a little difficult. All right, because essentially, we're going to be taking everything from the first 20 lectures, everything that you've learned thus far in the entire course, and it's all going to come together as we talk about reactions, and we're going to start talking about how the reactions use those principles to actually create chemistry, right? And so the first reaction we're going to learn about is called radical halogenation. And it's one that I would say is not as normal as the other ones that we're going to talk about, but it will set the stage because it will give us a lot of principles that we can use to then further the way that we look at things as we move into what we call the big four. So for radical halogenation, the first thing that we're actually going to talk about is what we call classifying carbon substitution. All right, and what this is it is a way for us to identify when different carbons are going to stabilize things more. All right, but the way carbon substitution works is essentially the substitution number just indicates the number of carbons that are connected to that carbon. All right. And so this is very helpful whenever we're talking about things like hyperconjugation stabilization, right? And the reason we'll look at in just a second, but essentially, the way that the substitution number works is you can imagine it just indicates the number of carbons connected. And we have four different ways that we can classify something because a carbon can have up to four different carbons attached to it. So we have primary, right? Or you'll notice that we'll also write these with a number with a degree sign beside it, right? So this would be the one with the degree sign. Primary carbons are those that are just attached to one other carbon, right? So you can imagine these ones on the end here, these CH3s, they have a single bond to the carbon in the middle, so both of them are considered primary. All right, but the carbon in the middle has two bonds to it, right? Two bonds to carbons, at least, because remember that this substitution pattern is only indicating number of carbons, not anything else. So the one in the middle we would classify as secondary, right? Because it has two carbons connected to that carbon. Okay, so that would be an example of a secondary carbon. Further, if we had three carbons connected, that would be considered a tertiary carbon, right? So that would be something like this here, where this carbon right in the middle here has three carbons connected to it and one hydrogen connected to it. And then last but not least, we have quaternary, which is when a carbon has four different carbons connected to it, right? So something like this carbon in the middle here would be considered quaternary. Okay. And so we use this type of substitution number to actually help us describe what type of carbon we are working with. All right. But keep in mind, once again, I'll restate it, it does not account for things that are not carbon. All right. And so a way to actually show this is if you think about something like isopropanol, right? The carbon in the middle is secondary, right? Also known as that little 2 with the degree symbol. It is still secondary because that carbon is connected to two carbons, an oxygen and a hydrogen, right? But the oxygen does not count in its substitution pattern. So this is still just a secondary carbon, which means attached to it is a secondary alcohol, right? So it helps us identify things like this. The same thing goes for if we were looking at a structure that looks like this, right? We would say that the carbon here is tertiary, right? Because it only has three carbons connected to it, and the bromine doesn't count. Okay? So this whole idea of substitution, it helps us quickly identify stability, right? Because substitution sort of leads to it. And the way that we can visualize this is think about what we talked about at the very end of our last lecture, which was hyperconjugation. When we were talking about hyperconjugation, we said the more times something has hyperconjugation, the better off it is going to be, right, in terms of that radical. And so looking at something like this, right, if we're looking at this radical right here, we would say that it is attached to a primary carbon, right? And therefore that makes it a primary radical. Okay? And we know from this it does have one source of hyperconjugation, that being the methyl there, and that is the one carbon attached that makes it a primary radical. But then also, if we take a look at something like a tertiary radical, right, that would be something like this, we know that the tertiary radical is more stable due to more hyperconjugation. All right. So essentially, this idea of identifying these substitution patterns can help us more quickly say if something is going to be more stable, less stable, because you can also use it for carbocations. You can also use it for talking about functional groups, right? It's what we were looking at right up here. We would say that the one on the left here, this is a secondary alcohol, right? Because it is on a secondary carbon. We would say that this one on the right here, this is a tertiary alkyl bromide, right? Because the bromine is on a tertiary carbon. So knowing these substitution patterns, primary, secondary, tertiary, and quaternary, can help you more effectively communicate what you are trying to say when you're identifying things that are stable or functional groups. Okay? Now, that being said, looking at this idea of our substitution stability, this is just a reminder from last lecture. When we were looking at these radicals, the radical stability went something like this, right? But now we can word it in terms of the substitution patterns. We've got primaries are worse than secondaries, right? Secondaries are more stable. We would say that these primaries are the least stable radical, right? But then tertiaries are better than secondaries. And all of this is because each of these has increasing hyperconjugation stabilization. All right? Whoops, that's supposed to be an arrow. And then we also had said that hyperconjugation was not the only way to stabilize a radical, right? Even better than these are things that are resonance stabilized. But the thing is, we can also identify these in terms of their resonance, right? Because we would say a primary with resonance would be a little worse than a secondary with resonance, right? And this is all because, if you think about it, they can still have hyperconjugation even though they also have resonance. So, for example, the secondary with resonance is more stable than the primary with resonance because although both have resonance, the secondary also has hyperconjugation to stabilize it. Either way, top of the chain would be like a tertiary with resonance. All right, so overall, on the right side here, we have essentially a statement saying resonance is better than hyperconjugation. But in this series, it is still increasing hyperconjugation stabilization. All right. And so that leaves us with being able to say that this tertiary with resonance is one of the most stable radicals. All right. So with that being said, we're going to move into our reaction for today, which has everything to do with radicals and radical stability, which is why we prefaced it with this. And that is a reaction that is called radical halogenation, right? And so the name implies to us that it is a reaction that involves radicals, and halogenation, all this means is that we're essentially performing an addition of a halogen. And as a reminder, our halogens are fluorine, chlorine, bromine, and iodine. All right. And so we're going to do an example reaction of this looking at bromine. So what is going on in this reaction here? It has technically four different reagents. The first one is just a general alkane, right? Unsubstituted in terms of functional groups, just a normal alkane. So in this case, we're looking at 2-methylbutane. All right. And as a matter of fact, this is one of the only reactions that alkanes can do. So practically speaking, if you see an alkane as a reagent, hint, it might actually be a radical halogenation that you're looking at. The second reagent that we have is our source of the halogen, right? And this is always going to be the diatomic elemental halogen, right? And so in this case, it's Br2. But if we wanted to add chlorine, we would be using Cl2, fluorine, F2, iodine, I2. Okay? The next reagent is this weird H nu, all right, which kind of looks like HV. And what this is light. All right. We'll talk about what that's useful for in a second, but it is necessary for this reaction to go well. You could also substitute it for heat if you want to. And then the last reagent is the CBr4, and this right here is just a solvent. Okay? And so solvent, what we're talking about when we talk about solvent, it's the same as the Gen Chem definition. It is just what the reaction occurs in, and it shouldn't affect or well, I guess it shouldn't be used as a reagent. Or I guess reactant would be a better way to say it, because essentially it's not actually reacting, it's just there to facilitate the reaction occurring. What happens is when this reaction occurs, our alkane gets halogenated. It has the addition of a halogen occur. And in this case, it's going to go to that position right there. All right. And this is what we would call our major product. And anytime you see the words major product, you just need to think to yourself, this is the product formed in highest percentage. So right off the bat, this may look like a mystery. But what we're going to do is we're going to start peeling back all of the layers of this in order to understand exactly how this reaction is occurring. And the way we're going to do that is through what's called a reaction mechanism. And mechanisms are going to be the bread and butter of the rest of organic chemistry 1. So hopefully you get used to them from here on out because they are incredibly important. So what is a mechanism? Well, a mechanism is essentially a step-by-step guide of what is happening in the reaction, right? A better definition would be a set of reaction steps with arrows that show how the reactants are converted to products. All right? And you can think of this as pretty much an instruction guide. Okay? It is saying if this happens, this will occur, right? And so every reaction has a mechanism. And as a matter of fact, you've already seen some mechanisms in the past, right? For example, we've already seen an acid-base chemistry mechanism, right? We just didn't fully define it as such beforehand because it's just a single step, right? It's something like an acid-base chemistry mechanism would be, for example, taking water and HCl and making H3O plus and Cl minus, right? We showed this mechanism before as a lone pair of electrons from the oxygen grabs the proton and you break the bond between the hydrogen and the chlorine, right? This is technically a mechanism. And the most important part about your mechanism, of course, is the electron flow arrows. All right, because these are showing the bonds broken and formed. Okay, so with that being said, let's take a look at the radical halogenation mechanism because it's a little more complicated. All right, so we are going to use the mechanism for the reaction that we drew up above. All right, because it is going to be the reaction that this entire lecture kind of hinges on. So, first thing that's going to happen in our radical halogenation mechanism is what is called initiation. Okay? An initiation is the step in which the light comes into play. Okay? So essentially what happens is the bromine is just chilling out, minding its own business. Okay? And out of nowhere, light comes in and it hits this bond. It can also be heat that breaks it. But essentially, what's going to happen is enough energy is going to be given to that bond that it's going to break in half. Okay? And so, if you remember from last lecture, we talked about homolytic bond cleavages. This is an example of a homolytic bond cleavage, where both bromines are going to receive one electron. So, remember, to show one electron, we are showing the single-headed electron flow arrow. Okay? Because that's showing only one electron moving. What that does, and this is an initiation step, is it generates two bromine radicals, right? It makes Br dot and Br dot. Once this has happened, the reaction has started, hence why we call it initiation. But the reaction continues through a step called propagation. And there's actually two propagation steps. We're going to talk about propagation one first because it's technically the first one that happens. Now, in this step of the mechanism, essentially what's happening is one of those bromine radicals from the first step is going to show up and it's going to bump into our alkane, right? And what that's going to do is there are hydrogens all over this alkane. The bromine's going to take one of its electrons and form a bond with the hydrogen, right? And so to form a bond with the hydrogen also needs to provide one electron. Where's it going to get that from? From the bond between it and the carbon. All right, so this is going to form a bromine hydrogen bond, all right, which is very stable. At the same time as this happening, that CH bond is breaking and one electron is staying behind with the carbon, right? Because the other one went to form that hydrogen bromine bond. So in the end, what we see is that we now have this tertiary radical, right? Because we just found out how to name these, right? We've made a tertiary radical and we've made HBr. So that's good. Then we run into the point where now that we have a carbon radical, it wants to make a bond with the bromine. Because remember, the bromine ends up on that carbon at the end of the reaction. So this is where propagation 2 comes into play. How this works is essentially the alkane with in this case, the tertiary radical, is going to come into contact with another molecule of Br2. And what's going to happen is the carbon is going to give one electron to form a bond with one of the bromines, which is going to need to give one electron. That electron is going to come from that bond, so that tells us that the other electron is going to have to be left with the other bromine. So at this point, we now have our products, right? We have HBr and we have the alkyl bromide that we had originally shown up here is our major product. All right, I guess I should put plus HBr. Here's the thing though. In the propagation step, we left a single bromine radical around, right? And the reason for this is this reaction actually continues, right? It can do this propagation over and over again because then this bromine that we formed can come back around and it can act as the bromine in this step up here, right? It can continue the propagation. Now, with that being said, I want to make it very clear that for this step, it just continues the reaction. So ignore it in energy diagrams. It will get very confusing if you try not to ignore it, just because essentially um, you'll have to continuously try and balance the reaction, and this extra bromine radical will never be balanced. Now, that being said, there is a way that the reaction ends, because there has to be, and that is through the step called termination. And this one you will want to include in your energy diagram, because essentially what happens here is the most common way that the reaction is terminated is that you have two radicals. It can be any two radicals, but for the sake of this class, we are going to show it as the ones that make the product we want. Okay? And what they do is they just come together and they form a bond, right? So in this case, a carbon radical and a bromine radical come together and they make the carbon-bromine bond. And that is the end of our reaction mechanism. So there's technically four steps: initiation, propagation one, propagation two, and termination, right? And you need to be able to know and show all of these steps as they are. Okay? So I will let you know right now, this mechanism will likely be on your exam. Okay? So please make sure that you take the time to actually learn it and understand it. Okay? Now then, that being said, you might notice in propagation one that we take a hydrogen from the alkane, right? But the thing is, if we were to look at this alkane just in a general sense, that's not the only hydrogen that exists, right? We have that hydrogen, which I'll show here in blue. We have a bunch of hydrogens that are surrounding it, right? I'll show these ones all in red here. We have some over here, and then we have some more over here. I've colored these the way I have because essentially these all show the different types of hydrogens that there are, right? The ones in red are the exact same because they're kind of symmetric in terms of both being off primaries. Oranges are secondaries, the pinks are a couple primaries, and then we have the blue, which is a tertiary. So why is it that the blue hydrogen is the one that gets taken and not any of the others? Well, to understand that, we have to first calculate the reaction energy, aka the reaction enthalpy. Okay, for doing this, the first thing that we need to do is we need to say, what is reaction enthalpy? Well, we talked about enthalpy a lot last time in terms of thermodynamics, but essentially the enthalpy of reaction can always be calculated in a very simple way. That is, delta H for the reaction is equal to the energy of bonds broken minus the energy of bonds formed. You may remember this from Gen Chem, because you did talk about it quite a bit back then, but essentially it's the exact same formula, but we can use it here to help us talk about the enthalpy and the thermodynamics of this reaction. Now, that being said, I would like to throw out there that in order to do these are all homolytic bond cleavages, right? They all split apart and each side gets one electron. You're going to need to use the BDE table, right? And so BDEs, just if you wanted to know where all of them are, because I will give a very truncated list, they are on page 204 of the textbook. Okay, so look there if you are ever doing other problems and you need to get BDEs for them. Okay, for this reaction specifically, right, we are going to show the reaction in its full form, and we are going to calculate the overall reaction enthalpy just using what we have available to us. So, this is a little more detailed than the reaction scheme that I had given before, but overall it is still the same idea. We are going from the alkane with Br2 to make the alkyl bromide and HBr. So first we have to ask ourselves, what bonds are broken? Well, we know during the reaction that the bond between the carbon and the hydrogen gets broken, and we know in initiation the bond between the two bromines is broken. Other than that, if you look through our mechanism, no other bonds end up getting broken, except for in propagation 2, which you will need to ignore because essentially that one's just doing it over and over again. And so with that being said, those are the only two bonds that we break, so those are going to be the only bonds that we have to calculate the energy for. On the other side, we have our bonds formed, right, which is the second part of our delta H. We form a carbon-bromine bond, and we form the hydrogen bromine bond. So these two bonds that we form are also going to have their energies calculated. So looking at the bonds broken, right, we have two of them. That would be the tertiary CH, right? Because remember when we talked about bond association energy last time, it does matter which carbon the radical ends up on, because the more hyperconjugation, the more stabilized it's going to be. So in this case, a tertiary CH bond has a BDE of 91 kcal per mole, and then the bromine-bromine bond has a 46 kcal per mole BDE. Okay? That means our total energy of bonds broken is going to be 137 kilocalories per mole. Okay? On the other hand, for our bonds formed, we're looking at a tertiary carbon-bromine bond. Funny enough, this also is different from a primary carbon-bromine bond, right? Something like that is very different. They have different bond association energies. So in this case, the bond association energy for this bond is 65 kcal per mole. All right. So remember, bond association energy does relate to the bond strength. So if we compare that CBr versus the CH bond in this case, the CH bond is much stronger. All right. But the beneficial bond that is formed is that of the HBr bond, because this one has a bond association energy of 88 kcals per mole. Right? So our energy of bonds formed is 153 kcals per mole. So with those two numbers in hand, we can calculate our delta H of reaction, right? So our delta H of reaction would be the bonds broken minus bonds formed. So it would be 137 kcal per mole minus 153 kcal per mole. And of course, that ends up giving us a delta H of the reaction that's equal to negative 16 kilocalories per mole. And that tells us that this reaction is thermodynamically favorable. All right, and it is actually exothermic. All right. But what about those other carbon-hydrogen bonds, right? Surely those are going to have different enthalpy of reactions, right? Because those are going to have different values for our bonds broken and bonds formed right here. So taking a look at that idea, right? It's not the only product, right? So if we were to ask ourselves the question, is it the only product? The answer would be technically no. Because if you take this and we throw it in here and we do this bromine, light, and CBr4, we would end up getting the product that we saw, right, on the tertiary position. We could get a product on the secondary position. We could get a product on the end primary position there, or we can get the product on one of these primary positions here. So this overall is four different products. And we know that the first one was formed in the highest percentage. But the question is, does the thermodynamics support that idea? Right? Is it true that thermodynamically this one would be the most favored? Well, I went through and I calculated these delta H's of reaction, and here's what you find if you were to take the time to do that. We already know from the calculation we did up there that the delta H of reaction for this one is negative 16 kilocalories per mole. All right. On the other hand, as we start to move down the line, so the secondary has a delta H of reaction that's negative 15 kilocalories per mole. That's not much different. As a matter of fact, that's barely different enough to support that one would be in so much more percentage than the other. Right? Furthermore, if we take a look down the line, these two primary ones share relatively the same energies, and both of their delta H reactions are negative 12 kilocalories per mole. All right. Now this can actually afford a little bit more wiggle room because it's not like they're just a single kilocalorie from the tertiary. They're three, which is relatively different. But here's the thing, right? Even though this is the thermodynamically favored product, it's not by much, right? We would expect, in terms of the relationship between this and the one directly to the right of it with the secondary carbon, we would say that it's pretty close to a 50-50 mix, or at least should be for this, right? And so what we find is that maybe it's not about the thermodynamics, right? So what we're going to do is we're going to take a look at some activation energies. Well, if we think about each of these reactions and where activation energy matters, right? What we would see is the initiation for each of these should be the exact same, right? Propagation is when things change because remember, it's in that propagation one step that the hydrogen is actually pulled away from the carbon. So the question is, all right, what does that look like in terms of our activation energy? Well, in terms of activation energy, if we were to take the alkane, throw it in with this Br dot, on the tertiary position, we would see an activation energy, an EA, of approximately 10 kilocalories per mole. Okay, that's pretty interesting, right? Because that's a pretty high activation energy, but it's not too bad. Next up, though, if we did it the same way, but this were to go and grab from the secondary position, the activation energy is actually now about 13 kilocalories per mole. Okay, so we would say that the tertiary position is actually faster because it has a lower activation energy. All right, but what about the primary position? Well, the primary position, this is true for all of them, but I'm only going to show this one. Oh, whoops. Essentially, it follows the same trend, right? Where its activation energy is about 16 kilocalories per mole. So clearly, the reaction up top here is the fastest radical halogenation for this molecule. But here's the thing. It's not always true that the thermodynamics and the kinetics line up, right? We could have had an activation energy that was completely the opposite. It could be higher. So we kind of have to ask ourselves, why is the activation energy so low? Well, what we'll need to do first is in order to answer that question, we're going to need to draw an energy diagram. Okay? And so for this energy diagram, we are going to be comparing what the energies of each reaction look like. So for this diagram in particular, of course, it is still energy and reaction progress. But to help us out a little bit, we can split up the reaction progress into the different steps of the reaction. Where this first step is the initiation. Second step is where we see propagation 1. We ignore propagation 2 for our energy diagrams. And so we're just going to show the termination as the last step. So, first thing that we see is all of the reactants start out at the same value. Okay? And the reason for this is they're all just the Br2, right? Because initiation is just taking the Br2 and breaking it apart into the two bromine radicals. So this is going to be I1, or our first intermediate. From here, it's going to split up a little bit because the propagation step changes everything. All right. And how it's going to split up is we'll draw this in a couple different colors, right? So the blue trace will be that tertiary carbon that we were looking at, right? The red trace is going to be the secondary carbon that we're looking at. And then the yellow trace, or the orange trace, is going to be the primary carbon. So what do these look like in comparison to each other? Well, in terms of where they sit with one another, they're a little higher than the energy of I1, right? If we go back to the propagation step, which is right here, we're breaking the CH bond and we're forming the CB or the HBr bond. And if we look at our bonds broken, bonds formed, the HBr bond is at 88 kcals per mole, and then the CH bond is at 91. So it's about a plus 3 kcal per mole difference between the first intermediate and the second intermediate for the tertiary, right? That, of course, is also true of these other ones where they're a little higher, but they are even worse off in terms of enthalpy because they are all forming less stable radicals. But why does this matter in terms of activation energy? Well, it's because activation energy is dependent on transition state stability. All right, so I'm going to draw these traces real quick, and then we're going to talk about why they look the way they do. Right, so the blue trace is going to have the lowest activation energy, which we already saw up top. The red trace will have the second lowest, and then the orange trace will have the highest. All right, following this, for termination, we know that also all of these are going to have slightly different ending products, right? But they should all follow the same trend where they actually have about the exact same activation energy when leading into the products, which is not very much, right? It just really wants to go downhill here. But here's the thing. That activation energy is all the same. The activation energy is the step before, a little different. So, the reason this is different is because, of course, the activation energy is dependent on transition state stability. So that means we have to look at what the transition state actually looks like. Okay? So how do we know what the transition state looks like? Well, we found something last lecture that was very useful for that. It's called Hammond's postulate. And when we were looking at Hammond's postulate, we essentially said whatever the transition state is closer in energy with is what will actually be what the transition state looks like. And so in this case, our transition state for each of our traces is closer to the second intermediate, right? So we would say the transition state looks like intermediate number two. Okay. So thinking about this, this is the propagation step, right? And so I'll draw it out for the one that we were looking at beforehand. So we have the hydrogen, we have our Br radical. It's going to come around, it's going to get an electron from there. We're going to give one electron to that carbon. We end up with the alkyl radical and HBr. If we're drawing this transition state, right, what we would do, and we're going to draw this in the colors that we related to the diagram up top, is we're going to have a dotted line to the hydrogen, right, because that bond is being broken. And then there's the bromine hydrogen bond that is being formed. So we're going to have a dot to that. Now, when we're looking at these transition states, there are not charges, but there are radicals. And partial radicals do exist. So we have to include the fact that there's a partial radical on the bromine, and there is a partial radical on the carbon. Now, when we're thinking about this in terms of Hammond's postulate, remember that's in terms of the bond lengths. So looking at this in the, if it looks like these products here, right? This is what the transition state looks like. Essentially, we're saying the HBr is associated, so that bond should be short, and then the carbon with the radical is in the, I guess the CH in that case is dissociated, so it is long. All right. And we can do the same idea with all of the other drawings, right? The only difference is the hydrogen that is being pulled off. So we can put partial radicals on things, and we can show that in each case, the hydrogen bromine bond is short, and then the hydrogen carbon bond is long. All right. And then same thing with our last one, the orange trace. We have our carbon-hydrogen bond breaking, that HBr bond forming, and then, of course, with some partial radicals. And we know that just like the other cases, that CH bond is long, the HBr bond is short. So, what does this have to do with transition state stability, right? Everything we've talked about so far is the same stuff we talked about last time. But in this case, you have to think about it in terms of what these look like. All right. What we're essentially saying is if it looks like the products and that CH bond is long, that means in each of these cases, there is more radical on the carbon than the bromine. And why does this matter? Well, it matters because different carbons have different radical stabilities. Right? So it's actually the same reason for thermodynamics here as we can describe how the activation energies sit here. Essentially, what we're looking at is in the first case, we have what is most like a tertiary radical for our transition state. Right? In the second case, we're saying we practically have a secondary radical as our transition state. And in the third case, we're saying we have a primary radical as our transition state. All right. And so what this is showing us is that it's always true that tertiary is better than secondary, which is better than primary for radical stability. But it's also true that tertiary is better than secondary is better than primary for transition state stability. All right. So when we're looking at our energy diagram up here, right? That's why our energies for our transition states differ like this. Of course, the primary is going to be the highest because it's essentially a primary radical in our transition state. All right. Of course, the tertiary is going to be the most stable because it looks like a tertiary radical in our transition state. Now, that being said, if you think about this as some guy who wants to climb up a mountain, right, starting down here at the reactants, the question is, which path would he take? And the answer to that's pretty simple. He's going to take the one that is of least resistance. So he's going to follow the blue path. Going to go up the mountain here, then up this way because this has the smallest peak, right? And so it's easier to get over that peak, which means the reaction is faster, which means it's going to follow that path. And that is why we actually get more selectively the tertiary than the secondary and the primary. But the question is how selective, right? And it might surprise you because earlier when we were looking at thermodynamics, it looked like it should be about a 50-50 mixture, right? But if we're looking at selectivity of halogenation, right, we can start by looking at bromine. All right, so let's say bromination. What would our ratio of tertiary to secondary to primary actually end up being? And well, people have gone through and calculated this in the past. And what they found is that for every one primary bromide that is formed, there are 99 secondaries that are formed. All right. But also, there are 1,600 tertiary bromides that are formed. Okay, so that's essentially saying to us, if we ran this reaction and we were looking through the products of it, we would find that for every one of these formed, so for every one of these, there is 1,600 of the major product that we had talked about. Okay? Here's the thing though, and this is where things get a little more confusing. It's the fact that chlorination, right, which is just taking chlorine, does not have the same selectivity. Funny enough, chlorine is for every one primary, there are 3.6 secondaries. There are only 5 tertiaries. So if we're looking at this, this is much less selective. But why? If you want to think about it, take a second to actually um, look at these and try and figure out exactly why. But if you would like to know the answer now, we'll go through it. Essentially, for this chlorination, let's try and do the exact same chlorination that we were looking at as we did the bromination, right? So the only difference here is everywhere that there was bromine and the other reaction, we are replacing that with chlorine here. So instead of CBr4 as our solvent, we're going to use CCl4. All right, it'll still make the same mixtures of products. We can still get 4 different products with chlorines on them. I'm only going to draw out 3 of them, so I'm not going to draw out the other primary because there's multiple positions. But essentially, if you were to take these and do the delta H reaction, what you'd find is that for the chlorine on the tertiary position, it's negative 33 kilocalories per mole. Now compare that to the old bromine, which was about 16 kcal per mole, and you'll find that this is about twice as favorable as the bromine. But that doesn't really explain anything, right? Because we can take a look at this secondary. The delta H reaction here is negative 30 kcal per mole. Okay, so not that much different, especially not whenever you consider the delta H reaction of the chlorine to be negative 28 kcal per mole. Now, these are all pretty close, and at this point, whenever you get this low in reaction enthalpy, there's not much of a difference, right? We can say that this is practically the same as the enthalpy for the bromination in terms of difference, right? So practically the same. If we were to look at an energy diagram, though, and this will just be the energy diagram of the overall reactions, what we'll find is we can do the exact same one that we did for the bromination, where we split it up into the different pieces. So the first part will still be initiation. Then we'll do propagation 1 and termination. And we'll do the same idea, where blue is for the tertiary, red is for the secondary, and orange is for the primary. If we were to look at these, it remains the same between the two, that your starting reactants go uphill during the initiation step to make the first intermediate. But then from here, something interesting happens, right? In this case, we are making an HCl bond and breaking a CH bond. HCl is a much stronger bond than HBr. So what we see in this case is that RI2 is actually thermodynamically favored in comparison to, if you remember our reaction coordinate diagram for bromine, it's actually endothermic for this step. The fact that it's exothermic down here for the chlorination matters a lot, because what we end up seeing is that the reaction's activation energy, even though the final enthalpy is a little different, like we see in that up there, notice how those activation energies are about the same, right? And it's true at the end, whenever we go through termination, that these follow kind of the same route as the radical bromination, where they all kind of do their own thing and they fall down, and they have about the exact same activation energies. So why is it in this case the activation energy between I1 and I2 is so much lower? Well, to answer that, we once again have to use Hammond's postulate, right? So looking at this transition state, where is it closest to? Well, in this case, it's closer to I1. So this actually looks like the first set of intermediates. Okay? So looking at this type of reaction, we are going to once again show the propagation step. In this case, it's still the same, where it's the chlorine grabbing the hydrogen, making the HCl bond, and forming the carbon radical. But we know energetically it is different. And so when we're looking at the transition state here, what we see is that in this case, the fact that it looks like the reactants means that, unlike in our radical bromination, where the CH bond was long and the HBr bond was short, it actually swaps. The ClH bond is short, and then the HC bond, the CH bond. Oh, sorry. I meant to say it is the HCl bond is long and the CH bond is short. All right. And notice that this means that essentially we are talking about this transition state looking a lot more like a chlorine radical. But how does that differ between the other secondary and primaries? Well, funny enough, the secondary transition state kind of looks a lot like a chlorine radical. And remember, these are not ways to draw transition states. This is just shorthand to help you all understand. So please don't draw them like this on the exam. But it kind of looks like a chlorine radical. And then on the primary, it kind of looks like a chlorine radical, right? So this transition state here, all of them are relatively close in energy because each one looks kind of like mostly a chlorine radical. The differences in energy for those activation energies, right? Because notice they are still like slightly different. They have little gaps in between. Well, the reasoning for that is because there is still some um, alkyl radical present, right? Some of this exists, but it primarily exists as a chlorine radical. So essentially what that means is that since the radical exists almost as Cl dot for all three transition states, there's practically no difference. And so that is what leads us to the fact that chlorine is very not selective, right? Because even though the tertiary position is technically kinetically favored, it is technically thermodynamically favored. It's not by very much, and so it ends up being about a 5 to 1 in comparison to the primary position. Okay? All of that being said, chlorination we will not look at for the most part in this course for doing radical halogenations. We're going to mostly stick to bromine because in the case of bromine, you can predict what is going to occur, right? So with that being said, predicting how these reactions are going to work is very important. Okay, but what about iodine and fluorine, right? Well, for iodine and fluorine, essentially what we see is that both of these also aren't going to matter. All right. The reason is I2, right? If you wanted to run the reaction with iodine, it's too disfavored. Okay. Practically a tertiary iodination should be relatively easy, right? Because it should be a favorable radical that you're forming on a tertiary carbon, so on and so forth. Even then, the delta H of that reaction is +6 kcals per mole, right? It's endothermic. It is very difficult to get an iodination to run like this. Now, that being said, what about fluorine? Right, fluorine forms pretty strong bonds. And so theoretically, when we were looking at the difference between bromine and chlorine, chlorine was more favorable. So shouldn't fluorine also be more favorable? Well, the issue is that fluorine is not selective at all for the same reason as chlorine. It's so favorable that the transition state just practically looks like F dot. The other thing is it's also explosive. So for practical reasons, we won't see this actually happen in this course. We will only practically see brominations because the delta H reaction here, yeah, if you noticed above, we were looking at like -16, -30. Well, this is -113 kcals per mole for a tertiary carbon. That's a lot of energy. So because of the fact that this is ridiculously non-selective, practically everything's a one-to-one, and the fact that it's explosive, we're not going to focus on it in this course. We're only going to focus on the things that are actually useful in terms of reactions. So that being said, let's look back at bromination and let's talk a little bit about stereochemistry. So stereochemistry of radical brominations is quite interesting because essentially, if you think about it, if we were to take butane and run a radical bromination, and I were to ask what the product is going to be, well, the first thing you would think of is, okay, well, essentially, um, we have a couple secondary positions, a couple of primary positions. In terms of which one's going to be more favorable, we know based on all the things that we've talked about so far that secondary is a 99 to 1 favorability over primary. So what that means is in this case, our product should put the bromine on the secondary position, right? That should be our major product. Because of course there will be some of the primary around, but not enough for us to care. The other thing that we see is that what we've done now is notice that beforehand, this was just a CH2, right? So it was over here achiral. But now that we've done this to it, we've added another group. This is now chiral. So the question becomes, how do we know if it's wedged or dashed? And the answer is we actually have to look at what is happening in our reaction. So we're going to go through each step and we're going to think about, is this going to matter for our stereochemistry? First one is initiation, right? For initiation, it's just bromine, bromine splitting apart. This isn't going to make a difference for our stereochemistry because we haven't created a chiral center yet. The second step, which is propagation one, right? What's going to happen is one of those hydrogens is going to be pulled away by a bromine radical, right? It's going to form a bond to it, and then we're going to get the carbon-centered radical plus HBr. So at this point, we have now affected the stereochemistry, right? Because now we've taken away one of those groups that is the same. But a radical, as we know, is sp2 hybridized, right? Remember that we talked about this last lecture when we talked about hyperconjugation. It stabilizes the radical and it has to have the radical in a p orbital to do so. So it puts it in a p orbital, meaning it's sp2 hybridized. Now then, so sp2 hybridized things are flat, so it doesn't matter for wedges or dashes. What about in propagation 2? Well, in the second propagation step, that radical that we have formed comes in contact with some Br2 and it forms a bond. Whoops. Right, and that bond is where suddenly we become sp3 hybridized once again and chiral. So clearly, it is at this point in the reaction mechanism, it's at propagation 2 or termination, because both of them share the same bond formation. Um, we are going to see the chirality and the stereochemistry appear here. But the question is, which is it? Is it wedged or dashed? And the answer to that is it depends on the side of attack. All right. So we already recognize that this radical right here is sp2 due to hyperconjugation. All right. But here's the thing. Since it's sp2, that means it is trigonal planar. But the important part is the p orbital is above and below the plane. So if we were to draw this out, what we would see is the carbon is sitting here with a p orbital facing up and down. And we have these three other groups attached to it. Right? I'm just going to label them as R right now because it doesn't make a difference which group is which. And the radical could be residing above, or it could be residing below on the bottom side of the p orbital. Essentially, what this means is that when the bromine comes around, right, let's just assume it is the termination step to make our life a little easier to where we don't have to draw as much. When the bromine comes around with its radical, it can either come in and pair and form a bond on the top side, right? So we would call that a top side attack in this case because the bromine's coming in and kind of attacking the carbon, as you may call it. Or it can form the bond on the bottom side. All right. And we would say that these two are a little different from one another because this, of course, is from the top. This one is from the bottom. And what these do is if it attacks from the top, what we see is that the bromine is now pointed straight up. All right. And this R group that's off to the side, now you may notice that's a 90-degree angle. Okay. So it does not like to be in that position. Now, that being said, these other two R groups are also at really bad angles. So we're going to label these as RB, RA, and this one can be RC. And so essentially what it does is it tries to correct the bond angles as quickly as possible. And how's it going to do that? Well, what it's going to do is it's going to push RA back to be flat and plane, which is going to push the bromine forward. All right. So essentially what we're saying is that this goes backward. And just like all the others, whenever you rotate one thing, other things will rotate. The bromine bond goes forward. All right. And upon doing this rotation, what you may notice is now that carbon has RC in plane. We pushed RA back to also be in plane, which pushed the bromine forward, right, to put it on a wedge. And still in the back, not really affected by much, was RB. Okay? So notice that in this case, it has formed the wedge bromine. All right? For this other side, though, once it attacks from the bottom, it is pointing straight down. If we label all of our R groups the same way this time as we did last time, what we see is that essentially RA is now once again moving to go flat with the page, right? It's trying to force itself back into the page, which is also pushing bromine backwards as well. What this is doing is it is in turn pushing RB forward. All right. So this guy is going back to becoming flat. RB is going forward, and BR is going backward. And essentially what this is doing is it is pushing it to where now, once again, we have RC and RA in plane, but the bromine got pushed onto the dash, and RB got pushed forward onto a wedge. So notice that, and this is just to show exactly how it works, but notice it's very simple. If it is attacking from the top side, it becomes wedged. If it is attacking from the bottom side, it becomes dashed. Okay? So we can briefly just say that top attack gives us the wedged BR, and then bottom attack gives us the dashed BR. All right? But the question is, which one is favorable? Very simply, it's a 50-50 shot, right? Because if this thing is flat, and the p orbital just has the radical in it, and it's not really preferring anything, essentially the bromine can go for the top side, or it can go for the bottom side, and there is no preference. All right? So it's a 50-50 shot at what it's going to form. And we know that if we take something, so let's look at this reaction with stereochemistry involved. From a couple lectures ago, the optical rotation one, we talked about how, all right, if it's got a 50-50 shot, it's going to go right here, where 50% of the product is on the wedge, or it's going to go to where 50% of the product is on the dash. And that is also known as just a straight line to the bromine because it is a racemic mixture of enantiomers. Okay? So overall, we have a couple things that we talked about that were really important. And I did want to give a summary because I know this lecture had a lot in it. All right. So we're just gonna do a little summary here. First one is that BDEs, right, which we talked about last lecture and this one, they are directly related to radical stability. That being said, a more stable radical indicates a weaker bond, aka a lower delta H. Also, radical halogenation, specifically radical bromination, will always form the product with the most stable radical position. All right, so it forms the major product. With that being said, we know that radical chlorination doesn't always. And as a reminder of why that is, it's due to the Hammond's postulate and everything that we had listed above. And then the very last thing I wanted to say was that radicals produce racemic mixtures, right? So 50-50 mix of wedge and dash. And overall, that is radical halogenation. Okay? It is a relatively useful reaction because it can take alkanes and it can add on halogens, which is going to become more useful as we start to look at the next reactions in our series here, which those are going to be substitution reactions, which are going to rely heavily on this concept. So we'll see you next time when we talk about SN2 and the way that this concept now ties into it and bringing everything from the course together into a single lecture. See you then.